How does a nuclear reactor work?
What?
It's a simple question.
It's hardly a simple answer.
Of course. You presume I'm too stupid to understand. So I'll restate. Tell me how a nuclear reactor works, or I'll have one of these soldiers throw you out of the helicopter.
Right, so we're going to be doing fusion, fission, and mass energy equivalents today. But I'll only promise to do it if you promise not to throw me out of the helicopter afterwards. So you should know by now, hopefully, that nuclear bombs and nuclear power stations release enormous amounts of energy from a very small amount of fuel. So the question you should be asking yourself is, where does all this energy come from? And it's a really, really important question. And fission and fusion, which we'll cover in a second, get their energy from pretty much the same source, even though they're kind of opposite reactions. And they get it from binding energy. Now, we're not going to get into Pauli exclusion or energy levels of neutrons and protons. We're going to be looking at just a simplified version in this lesson. So binding energy is the energy that's needed to completely separate the nucleus into the individual protons and neutrons. In other words, we completely disintegrate all of them away from each other. Or alternatively, it can be expressed as the energy released when those separate protons and neutrons join together to form a nucleus. So binding energy is a type of energy, but the way that we're interested in expressing it is the binding energy per, so the binding energy per nucleon, and remember the nucleons are the protons and the neutrons in the nucleus. So we can think of this binding energy as the energy required to keep this neutron, this nucleus together, this atom together. Now, why do we need that energy? We have this kind of idea of a nucleus as being kind of like this one on FET of uranium-235, where it's kind of this ball of marbles of protons and neutrons. In actual fact, it's kind of probably more like this. It's jiggling around. There are internal forces going on inside the nucleus. The protons want to be away from each other. The strong nuclear force is holding them together. The neutrons are along there for the, let's reset that, for the trip, but there is a sort of this back and forth, this tug of war inside the nucleus, as the forces, some of them want to pull the nucleus together, some of them want to rip it apart. So if we removed the binding energy, these protons here don't like each other and they're going to fly off. So the red ones are the protons. So because we obviously can't do that, we can't kind of click our fingers and just remove all of the protons. But without that binding energy, they are going to fly apart like that. It just looks kind of cool, I think. It's disintegrating. So once again, we reset it. So we apply all of that binding energy, we remove it, and if we reapply that binding energy to bring it back together, it's going to look like that. Okay. So like a lot of things, nuclei tend to be quite lazy. So they want to change into arrangements with a lower total energy, that is the energy inside that nucleus, but the highest binding energy per nucleon. So they want most of the energy to be in the form of binding energy. And if it can get more binding energy, it'll need less energy to keep it together, kind of paradoxically. And the difference in energy is the energy released. So if there is a change in the energy, it's probably going to be an increase in binding energy, but kind of offset by a decrease, a bigger decrease in the total internal energy inside the nucleus. That's not really well worded, but kind of you get the picture. So there is kinetic energy, there is energy holding it together, and the binding energy is that, and there is kinetic energy kind of wanting to be released. That's sort of potential energy inside that nucleus. And when we change those energies, that is energy which is released. So if we have a look at another sim, we see it really nicely in this kind of classic graph that I've had made up here. So here we have the total mass number. So this is protons plus neutrons, and this is the binding energy in mega electron volts. So it wants to be as high as it can. So it wants to be up here. When it's up here, the binding energy is doing all of the work, and the potential and the kinetic energy inside the nucleus is minimized. So here we have hydrogen. It wants to be here. So it's going to fuse together with other nuclei to minimize the internal energy inside the nucleus and maximize the binding energy. And to go from here to here, obviously there is quite a big change in energy. That energy is going to be released. It has to go somewhere, and it's going to be released. And it's going to be released in the form of radiation and heat. Okay, so this is for really light nuclei. It's going to want to fuse. It wants to get here. It wants to be around iron nickel. It's commonly said that iron 56 has the highest binding energy. In fact, it's nickel 62 has tiny amount more binding energy, but iron is very stable. So our planet, a lot of it has fused and has fused to the point of being iron. Once it's iron, it's stable. Okay, that's fusion. The other side here, we have fission. So here we have these really huge nuclei on this end, and they want to move here as well. So to do that, they need to lose nucleons. So they will fission, they will split apart, or they will spit out nucleons, protons and neutrons, or just split in half. They want to go there. So this difference here is going to be the difference in energy. Notice that the difference in energy here is huge. The difference in energy here is less. It's still an enormous amount of energy, but it's a different type of energy. This is fission energy from a fission reaction that you would get in a nuclear reactor or in a nuclear bomb. So in your assessment, a good answer for why do heavy and light nuclei release energy? Light nuclei release energy when they fuse because the resulting nucleus is more tightly bound. So there's more binding energy per nucleon and has a higher binding energy per nucleon. Heavy nuclei release energy when they split because the smaller nuclei that are produce more tightly bound nuclei and have a higher binding energy per nucleon. So it's not total binding energy, it's binding energy per nucleon. So let's talk about how we can explain this change in energy. And it really comes to a really famous equation that we'll get to. E equals mc squared. Now you may have seen that. It's probably the most famous equation in science, and it's Einstein's, it would be special relativity formula. So let's have a look at kind of what this means. So E here is energy. M here is mass. So this is the mass of the nucleus, or the nucleons themselves, really. C. What is C? C is the speed of light in a vacuum. And notice it's squared. Now, you just need to know that that is a huge number. The speed of light, for our purposes, is going to be 3.0 times 10 to the 8 meters per second. When we square that, we get 9.0 times 10 to the 16. A huge number. We can rewrite this equation to take into account a thing called mass defect. That was my washing machine starting there. Mass defect. Now, mass defect is going to be represented as delta M, change in M. So, mass defect in a spontaneous nuclear reaction, if you were to precisely weigh, like put the nucleons onto some sort of magic set of scales, and if you weighed the reactants, so what you had before, and then you weighed the product, and I know that weighing and mass are not necessarily the same thing, but we're going to say that there's kind of the same thing. The difference is not the mass is not going to be the same. Okay, I'll say that again. When you fuse or fission nuclei, the mass of those nuclei is not the same. It's going to change. And Einstein's great revelation, which is just so beautifully expressed in this equation here, is to say that this change in mass is going to be represented in a change in energy. And because c squared is such a huge, huge number, a really, really small change in mass is going to result in a really, really huge amount of energy released. And it's a loss of energy from that nucleon. It needs less energy to keep it together, less energy inside it. That energy is going to be released. So this change in mass is called the mass defect. So the mass hasn't vanished into nothing. It's being converted into energy. So there is an equivalence here between energy and mass. So energy is kind of equivalent to mass, and it's equivalent to mass by some constant, and that constant is the speed of light squared. Okay, let's have a look at some of the units that we're going to be working in. The unit that we're going to be working in, really, for us here, we're going to be using joules, say, but it's more common to use a thing called an electron volt. So an electron volt is the voltage required to move the charge of one electron over 1 volt, which is not a great deal of energy. It's related to joules in that is 1 coulomb of energy over 1 volt. But it doesn't make sense when we consider that these nucleon are so tiny. It doesn't make sense to have something as huge as joules, but we have something as an electron volt. And often we can see electron volts expressed as kilo electrovolts. It's 1,000 electrovolts. Mega electron volts, 1,000,000 electron volts, and on and on. Electron volt is a representation of energy. It's not a representation of charge. Okay, That said, how would we calculate the change in energy? So if we remember that energy that we're going to get is going to be the change in the mass times the square of light squared, and we're going to keep it in joules for now. The change in the mass is going to be represented by the mass initial, which is the mass of the reactant, minus the mass of the product, which is the final, if you want to kind of write it in those forms, minus the mass of the product, or really the products. And this is going to be all of them summed up minus all of them summed up. And the difference is going to be in form of energy times the square of light squared. So if the change was, let's say, 1.2 kilograms, which is going to be a lot of energy, 1.2 kilograms change. So we started with 3.2 kilograms of uranium 235, and we ended up with 2.0 kilograms of uranium 235. It's going to be a lot of energy. The change in mass is going to be 1.2 kilograms. So the amount of energy that's going to be released from that is going to be 1.2 kilograms times 9.0 times 10 to the power of 16. Now that is going to be a huge amount of energy. Let's work out how much energy that's going to be. So 1.2 times 9 times 10 to the power of 16 is going to be 1.08 times 10 to the power of 17 joule. 1.08 times 10 to the 17 joules. How much energy is that? Well, let's kind of work it out. It's going to be a lot of energy. Let's do a quick scan using our friend Wolfram Alpha. So 1.8 times 10 to the 17 joules. A lot. So 43.02 megatons. That's millions of tons of TNT. 1.123 to the times 10 to the power of 36 electron volts. A lot. But if we want to have a comparison for that, that's the New York City annual energy consumption. So that's the largest city in the United States for a whole year. And the total energy from the sun in 1 second, or 1.2 times the estimated energy released by Krakatoa, which is, I think, the largest documented eruption in history. A lot of energy. Of course, why doesn't all of that energy get released? Well, not all of the nuclei are reacted. So you're never going to have a totally efficient reaction. If you did, though, I mean, that's a lot of energy. All right, well, let's look at fusion and fission now. Let's look at fusion first. So fusion is nuclei together to form a new, heavier nucleus. And remember that nucleus that we form will only form if it will maximize the amount of binding energy it has, so to keep it together, and minimize the amount of energy inside the nucleus there. All right, so here we have, let's change that a bit. Let's kind of pretend that we can just look at two of these nuclei separately. These are separate ones here. We have deuterium, which is hydrogen 2. So deuterium is hydrogen 2, so it's going to have 1 proton, 1 neutron, and we can see that there. We see we have tritium, hydrogen 3. The 3 is pretty small, but tri meaning 3. So we have 1 proton, obviously 1 proton is hydrogen, 2 neutrons. This is not all that common, so this is a problem when would we want to make these. Okay, let's push these together and see what happens. So I'm going to bring them together, and they do not fuse. Okay, why did they not fuse? In order to fuse, they need to have a lot of energy, usually in the form of temperature, thermal energy, to push them together. So to do that, I'm going to raise the temperature of the plasma that we've made here, and this is going to be 10 million, 100 million degrees Kelvin. Pretty hot. Now when I bring them together, they're going to almost overcome that repulsion, but again be pushed apart. Okay, we can do a lot of things. We can increase the density, meaning that there's more of these things hitting each other, or we can increase the confinement time. That's the time that we give them to crash into each other. But let's increase the temperature, and let's increase it to 150 million degrees Kelvin. That's going to be a lot. And when we bring them together now, they're pushed together through a lot of energy, bam, and they fuse. These are the other nuclei fusing again. What have we made? We've made helium-4. So it's helium, 2 protons, 4 neutrons, 2 and 2 we see here. Notice that there is a difference here. We reset that. One of these neutrons is going to get spat out, and it's going to get spat out at a high degree of energy, and it's one of the reasons why the other ones start kind of popping. Let's reset it again when we bring them together. So it's going to be a self-sustaining reaction now. It's going to produce an awful lot of heat. All right, how much energy has been released? Well, we see here it's 3.5 mega electron volts. That's really the binding energy that's holding them per electron, that's holding them together, per nucleon, sorry. So the mass before was 5.03151 U, which is atomic mass units. The mass afterwards, if you see there, is slightly different. A tiny, tiny amount different. But remember, we're going to be multiplying that by the speed of light sound, speed of light sound, not speed of sound squared, speed of light squared. So the change is going to be a tiny amount, but when we multiply that, it's going to be, again, a tiny amount of energy, 2.8 times 10 to the negative 12 joules. But there's a lot of these. If we bring a lot of these things together, we're going to get a lot more energy out than we put into it. Remember, we have to put a lot of energy into it to get this plasma density and the magnetic field that it needs to fuse with each other, and to raise it to this enormous temperature. And that is one of the problems of fusion energy, that it takes a lot of energy to get the reaction before we can get energy out. It's a big hurdle, and it hasn't quite been solved yet. When it's solved, it's going to be a pretty good thing. Let's have a look now at fission. So fission, we have a pretty big nucleus. We're going to fire a slow-moving neutron at it. I'm not going to go into the reason why it has to be a slow-moving neutron. If it's fast-moving, it's going too fast to hit it. And it's going to have this sort of cross-section that it's going to hit. We're going to fire it. So the mass before is really, really big. We're going to fire it. It's got a lot of energy now. It's going to be split. So let's reset that again. We fire the neutron. There's an imbalance of energy. It's split. There is a release of energy. But look what else is released. We put a neutron in. it's going to spit out 3 neutrons again. Those neutrons themselves can go on and hit other uranium nuclei, and they can split and they will release 3 neutrons, well, an average of 3 neutrons. Those can go on and split, and that's what's meant by a chain reaction. Okay, let's watch it again. It hits, and watch the neutrons fly out. They fly out. Okay, the mass before was 236.05. The mass afterwards was 235.866. There is a mass difference of 0.18 atomic units, which is 3.09089 times 10 to the 28 kilograms. But remember, that's multiplied by the speed of light squared, so an enormous amount of energy is released. What does it split into? It's split into barium-141 and krypton-92. What's going to happen with these now? Well, let's look at barium-141, 141, sorry. It's going to be unstable. It has a half-life there of around about 18 minutes. So it's going to want to decay. One of the neutrons is going to become a proton, and it's going to spit out an electron. So it's going to be radioactive, and it's going to be N141. It's going to want to undergo beta negative decay again. Cerium-141, it wants to do it again, and now it's stable. All right, so let's reset this again, but now let's watch what's going to happen here. So it's going to move from here, and it's going to move. They're going to lose nucleons. Each of these nucleus is going to lose nucleons, and it's going to move towards a more stable state. So let's fire the neutrons. It's going to hit, and it's going to move that way. So this is fission. Fission is when we split nuclei apart. And here we have a picture of a sort of stereotypical nuclear chain reaction. It's a fission reaction. We have a neutron. It's fired at uranium-235. We're not going to go into reason why we use uranium. It's just inherently unstable. Well, it's easily fissible. There is going to be a fission. There is going to be a lot of energy released and radiation released. Barium and krypton are going to be ejected. Those are going to decay. They're not going to fission. One of these neutrons is going to fly off. There's going to be an average of 3 that fly off. It can hit another uranium nuclei, do the same thing again. Barium and krypton fly off. That in turn fires off more neutrons, and the chain goes and goes until we stop it, or until it sort of runs out of fuel, or these neutrons stop hitting other uranium nuclei. So here we have another sim. This is a fission chain reactor. So this is fairly common kind of diagram that you might get in your assessment. The neutron population is going to be 0. Now these are uranium-235 rods, and we're going to sort of almost imagine these as nuclei. Okay, here we have moderator rods. They act to stop the neutrons. So in a nuclear fission reactor, we want just a bit of reactants, but we don't want too much. So we do a couple of things to do that. We don't have the uranium higher grade, enough uranium-235 to have a chain reaction, explosive chain reaction, but we kind of really tightly control things in the reactor. All right, so let's have a look at how we're going to do that. We need to start it. So let's reset the core. Okay, and let's pull out some moderators and fire some neutrons. So we fire a neutron. These neutrons are going to fire around, not much is going to happen. So let's increase the effectiveness of the moderator. And again, not much is going to happen. There's going to be a bit of a chain reaction. All right, let's pull out these control rods then. Let's go crazy. Let's go full Chernobyl. Now we see a runaway chain reaction. So these neutrons are being created, they're being spat off, and they're hitting other nuclei. And the only way it's going to slow down is if we've run out of fuel. So if we stop refueling, this chain reaction is going to stop. These are, nothing is going to happen. Well, I mean, a lot's going to happen. But the radioactivity is going to decrease. If we start refueling now, we start putting more uranium in as it's being spent, the reaction starts again. And we can do quite a lot of things. We can put in moderator effectiveness. Moderator increases the chance of collisions. We would do this in Western reactors by water. The ones that you would see in the Chernobyl miniseries were a different beast. So we're changing water in there. Okay. Let's say that there is something crazy going on and we really want to stop this. We can scram that by pushing down the control rods, which effectively aim to stop the reaction, and we would pull out reaction, we would pull out fuel, and we would stop this sort of cedar neutron source. So we wouldn't be firing cedar neutrons in, and we see that dramatically the reactivity has dropped. Notice it's not going to stop. It's going to be quite difficult to stop these. There are still going to be neutrons flying around, and these are going to fizzle naturally, but it's a lot less than it was before. Our problem now is that the residual that's in here is going to be radioactive itself, and now the reactor has stalled. Now it's a dangerous, angry giant. We really don't want to get into this state unless we're decommissioning the power station, or we're changing the fuel or something like that. But it's stalled, and if we're going to pull it back up to full power, we're going to need to do it really slowly.
When nuclear fuel gets hotter, it gets less reactive. So fuel increases reactivity. Control rods and water reduce it. Steam increases it. The rise in temperature reduces it. This is the invisible dance that powers entire cities without smoke or flame. And it is beautiful.
So in the last part of the video, we're going to go over nuclear power. So when we are talking about nuclear power, really we're talking about converting nuclear power. So why do we have nuclear power stations? We don't have any in New Zealand, but there are lots and lots around the world, and there's over 100 being built around the world at the moment. Why would we have nuclear energy? Well, the reason that we have nuclear energy is not for to get nuclear energy, it's to get electricity, isn't it? So we need to find some way of converting nuclear energy somehow into electricity. I'm sure you don't want radiation coming down the wires into your home. And the way this is done is by harnessing nuclear fission. So currently there are no commercial nuclear fusion reactors for various reasons. It seems to be really hard thing to do. What does nuclear fission release? Well, it releases lots of heat, and that heat can become kinetic energy, which is movement, and that becomes the electricity. So let's have a look at what's actually going on here. So we start with uranium-235. So this is just one nuclei. We've done this one before, and we fire a slow-moving neutron at it. Obviously, there's going to be lots and lots and lots of this going on. It's not just one atom of uranium. So we're going to fire that on at it. It's going to have a really bad configuration in the nucleus, and it's going to blow apart. It's going to make us barium and krypton. Okay, but what else does it release? Well, we know that it releases those neutrinos, those neutrons, but it also releases lots and lots of heat. And I think that's shown as kind of that circle that's been released here. A lot of heat gets released. So how do we convert as a nuclear power plant? Let's just move that a little bit down. That's better. So here we have the actual reactor core itself, and that's sort of what we had here in the last part. We have a core. So these are uranium-235 pellets. These are the insertion rods. So these are designed as kind of brakes to stop the reaction. If we pull those control rods out and we increase the moderator effectiveness, then the moderator effectiveness are these things that are surrounding the uranium. Their job is to slow down the neutrons. If the neutrons are moving too fast, they won't have a good cross-section to hit. They won't have a good cross-section to hit the atoms. So this is why it's a slow neutron. So the moderator hits it, we slow it down, and it releases a lot of heat. So nothing is currently going on in this reactor. But if we fire a neutron, we're going to get that chain reaction. And now we're supercritical. We have too much going on. So we need to insert these brakes a little bit. It's overheating a little bit too much. And we introduce a steady trickle. So here's the amount of energy that's being released. And we start replacing that uranium until we get a really nice flow of neutrons. And it is a really, really delicate balancing business doing this. Change a little bit, and it's really, really difficult to get it at a sort of nice flat level. But this is what's going to happen. It's a supercritical. We don't want that, which means that there's more fissions than there are non-fissions. Now it's subcritical. We want it to be absolutely on critical. Oh, it's so there at it. Oh, nearly couldn't quite get it. It is a really, really delicate problem that we have. If we have a problem where we have increased the moderator effectiveness, let's do something really, really crazy, and we do that, we get a runaway reaction. This is really, really bad, and we have to hit the scram button. The scram button is sort of the brakes. It kills everything. It would, in a Western reactor, it would drain away. It would drain away the water that's surrounding the acts as the moderator. These boron rods here, and it's lowered really, really quickly. But even then, it still takes a little while for this to decrease in its energy. So all of these reactions are generating heat. So this is this bit here. So we've got the thermal energy being produced here in the reactor core. So here's here are the cores, the uranium core and the boron rods. And we have water going through it. Water does two things. It cools it, and it also acts as the moderator in Western reactors. In the Chernobyl one, they had a solid moderator, which was graphite, which is essentially just carbon rock, and it didn't really work that well, as we know. Okay, so we have the water. It goes into the core here, Obviously, there's 3,000 megawatts of thermal energy. That's a lot of energy. And it's going to superheat that water. And that water is going to go through it and it's going to come up here. The water, we don't want to use that water for two reasons. First off, it's radioactive. It's been in proximity to nuclear material. And also it's just way too hot. So it goes through a heat exchanger. Now the hot water goes through these pipes here and it's surrounded by colder water. So the waters never actually touch each other. That colder water is heated by the hot water and itself turns to steam very, very, very quickly. Of course, steam wants to occupy more volume than liquid. So that water becomes vapor, becomes gaseous water, and is pushed through this pipe here through a turbine, which spins, turns a generator, and makes electricity. That water has to go somewhere, so it's condensed back into steam. Some of it is sent here into the water cooling tower, which you'll see quite often in nuclear power stations. Quite a lot of people think that the cooling tower is the nuclear reactor. No, the cooling tower is exactly what you think it is. It's a cooling tower. There's water is sprayed into the top, the hot water, and air comes in through the bottom here. It cools it, it condenses here to the bottom, it turns back into water and goes around again. So this water cycle is going round and around and around that way. It's steam, it turns the turbine, it condenses back into water here, and then goes back again for another go. It goes around and around and around. This water here is doing two things. It's spinning. It's being spun by the coolant pump. We really want that water to keep going through. It's going to go through. It's going to be superheated and then heat up the other water, turn the turbine. We get electricity. Again, it's a really, really delicate operation. And if we have some problem, we can always scram it, the same as we did before. You see the power rods come back in, and even then, it's still not going to die away immediately. We have a very, very strong containment vessel. Now, this is something which was missing in Chernobyl. When Chernobyl exploded in 1986, the Soviet reactors did not have a containment vessel. They were two reasons. It was just too expensive, but also they were quite arrogant. They sort of believed that an RBMK does not explode. And yeah, it kind of does. By the way, it wasn't a nuclear explosion in Chernobyl. What happened was that they were having a test. They cut off this coolant pump. The reactor was not turned down properly. They did it all sorts of crazy things around it. There wasn't water going through the pump. It wasn't cooling. When they went to scram it, there was a sudden uptick in thermal energy that converted any water or a nuclear waste in there into thermal energy very, very quickly, and that blew the top off the reactor. So this core was exposed, and the thing that was previously in that core was on fire, and the smoke going up was radioactive. Not good. That's why we have a containment vessel. So that's what we've got. Essentially, we've got just a really, really spicy steam engine. Instead of a fire here, we have nuclear energy, and instead of, let's restart it, and instead of coal, we have uranium. We need this heat exchanger. Okay, so that's about it. Good luck.
I walked around the exterior of Building 4. I think there's graphite on the ground, in the rubble.
You didn't see graphite.
I did.
You didn't. You didn't! Because it's not there.
What?
Are you suggesting the core, what, exploded?